Section 2.4, an application which is digital logic circuits. And let's start by looking at black boxes and gates. So, as you might know in computers, all they really have are two numbers, ones and zeros, which we call bits. And while that's in computers, that is also true in basic circuitry as well. And we're going to think of these as our black boxes. So we've got some black box. We are inputting one or more signals, and we are getting out, though, a single output signal. And again, this black box is doing something to the one or more signals we're putting into it. All right, so as we look at these input-output possibilities and their resulting output, this is essentially going to be the exact same thing as our truth tables that we've seen earlier. The only difference is instead of putting trues and falses, we're going to put ones and zeros. And we're going to use 1 for true and 0 for false. So here you can see we've got our 3 inputs, for example. And again, we've got the inputs and outputs that are possible. And for this particular example, my one output of S has this result. Again, the ones are true, the zeros are false. So here, let's say we want to know what is the input when P is 1, Q is 0, and R is 1. I would just find that. It's the third row. And I would see here that the output S is 0. We do also sometimes call these gates. So our first one is the NOT gate or inverter. And this is basically the same thing as a NOT. So it will switch what we put in. Similarly, we've got an AND gate and an OR gate. And again, our values here will be the exact same thing as when we saw the truth tables for both the AND and the OR. We'll notice we do draw them a little differently. So the NOT looks like a triangle. The AND looks a little bit like a bullet. The OR, if you've ever seen like the fletching on an arrow, that's what the OR looks like. We will generally have the word written in there as well so you can see it. And you may not be able to see this very well, but hopefully you can see those output tables, which again do match up with the truth tables we saw earlier. All right, so we do have a couple rules for circuits, and you can see what those are going to look like. So let's look at making input-output tables for a circuit. So here we are going to give you a set of inputs, and we want to find out what happens. So here is my example. So here's the circuit I'm given, and I am told that my inputs are going to be P is 0 and Q is 1. So I'm going to move from left to right. So the P starts at 0, but the NOT is going to change it to a 1. So I'm putting 2 ones into an and that will give me a 1 out. So as you can see, R is 1. For B, and you can also see a quick little example here where we're writing the values, and we are then changing those values as we go along to see it more easily. So B, I've got a more complicated one, and my inputs, P is 1, Q is 0, and R is 1. And let's scroll down so we can see this one. Again, I'm usually going to put those numbers in there to see what happens. So I got 1 out of the OR, the NOT changes it to a 1, and then finally the AND, I get a 0 as my last result. Now, we might also be asked to do the full input-output table for a circuit. So here's a circuit, and basically I'd like all of the possibilities. So those are my 4 possibilities for P and Q, and we would work through that and determine that third one down would give me a 0, but everything else is going to give me a 1. Again, this is essentially the exact same thing as those truth tables that we did earlier. All right, we've also got something called a Boolean expression. And again, in logic, we could only get true or false. And so that is why we are going to call these Boolean, is because there's only 2 possible values. We can either get true, 1, or false, 0. And when we use these connectors, we do call it then a Boolean expression. So we've been looking at these before, but now we've seen the term Boolean. So we've got our circuit here, and what we would then like to do is write that out as that Boolean expression with all of the nots and ands and ors. So again, for this one, my option A, I'm just going to kind of, for each of them, I'm going to then write what it looks like in logic and slowly get it up. So here I've got P or Q in parentheses, and not, and then P and Q in parentheses. So this is our Boolean expression. And similarly, here's option B, where we've once again got that diagram, and we're going to follow it through, and I get in parentheses P and Q, and then and not R as I follow along. And then finally, a recognizer is a circuit that outputs 1 for exactly one particular output, and everything else is 0. So here would be an example. I've got 3 inputs, and you'll notice for all of my outputs, I only get a 1 for one of them. So this would be an example of a recognizer. And that is everything in section 2.4.